So I am Darren McGee, standing in this week for Ted Terracone. I am the director of the Institute for Energy Studies. And to those of you joining us online, thank you for being here. This is our part of our weekly speaker series. And this week, I'm super excited to welcome two graduates of the Institute for Energy Studies. They are joining us remotely. They are, I thought maybe on a spaceship, but it turns out they are down in Oregon. And I, as always, am thrilled to have this week's offering brought to you in partnership with my colleagues at the foundation, who make the behind-the-scenes wizardry of the technology work. So Hari Nath and Solomon Duke, like I said, both graduates of the Institute for Energy Studies. They both did the BS in Energy Science and Technology. They finished in 2023 and 2022, respectively. I think I got that right. Their careers in that brief 4 to 5 years, no, 3 to 4 years, have spanned everything from school bus electrification to data center energy efficiency work. And now they both find themselves working on industrial efficiency. And they're going to tell us a little bit about their path from Western to what they're doing now. And so I will turn the floor over to them without further ado.
Thanks, Darren.
Yep.
Yeah, thank you. I'll push just a moment. Oh, go back one. Oh, there's a delay. Oh, I'll skip the deleted slide. We got it. We got it. So here we're falling into frame, following like your energy use when you work with us. I just wanted to give a quick introduction. I'm Hari. Graduated in 2023, and Solomon is graduated in 2022. We're both engineers at Energy 350. Yeah. So a little bit about our story. So me, like Hari mentioned, I graduated in 2022 with a BS in Energy Science and Technology. While I was in college, I also interned at Sustainable Connections in their energy efficiency team to gain some early industry experience. And then after graduating, I did international energy peacebuilding research at the Center for Renewable Energy and Energy Conservation at the Arava Institute in Ktura, Israel. And this institute was really focused on using environmental issues as a bridge for building peace in the Middle East. And that really helped build my social understanding of energy. Then after that, I worked as the Pacific Northwest lead engineer at Northshore for 2.5 years, where I really developed my technical skills. Northshore is really focused on building a more sustainable internet by improving data center energy, water, and refrigerant use. And I wore a lot of hats here. So I got a lot of experience in the energy efficiency world, doing like energy auditing, energy modeling, commissioning and retrocommissioning, incentive management, policy compliance, construction management, and a lot of other elements of the energy efficiency world. And at first I had a lot of imposter syndrome because I was the only person in the engineering team without a mechanical engineering degree. But I quickly found that it didn't matter. You know, I learned the foundational skills that I needed at Western, and any technical knowledge I might have missed, I was able to learn on the job. And working at Northshore really built the framework for my engineering experience so that I could feel confident working on anything in the energy efficiency world. And now I work at Energy 350 as an SCM engineer, and I'll talk all about that later in this presentation. And if I could give any of tips for myself for starting in the technical engineering role without an engineering degree, it would be if you're having imposter syndrome among engineers, trust in your education and remember that you deserve to be where you are. Also, your energy education at Western will also teach you things that typical engineers don't learn, and that actually will give you a leg up in a lot of ways in the energy industry. And I recommend getting an energy internship while in college because it makes getting work after graduating a lot easier. And the main barrier that I noticed pursuing or working in the engineering field without an engineering degree is that you can't get certain accreditations as easily because they favor people with an ABET engineering degree. So like your FE, your PE, your professional engineering license, your CEM, you have to work longer to get those accreditations. So that's one way you're a little held back, but besides that, you're really prepared. I'll pass it on to Hari.
Yeah. Yeah, I graduated in 2023. In about 2021, I had kind of started in some informal internship slash just part-time job with the Washington State University Energy Program, which is a state-run kind of administrative, almost like public consulting organization in Olympia. And I was just working remotely. I was doing work on electric school bus electrification for tribes and school districts around the state. I was working with resource conservation managers to help them meet the Clean Buildings Performance Standard. And then I was also doing some very random projects like recycling of wind turbine blades and other random projects that the Department of Commerce would send our way. So I did that part-time while I was at Western. And then after I graduated, I took that as a full-time role as an energy analyst. And in that time, about a year and 8 months or so, I was kind of doing a more extended version of those projects. I was also doing community solar implementation and various projects. I started doing independent consulting as well with some people I'd met in the industry, just doing some energy load calcs for different people and writing up some very small reports and memos. And then I got a job very randomly at Energy 350. I saw it on LinkedIn. I applied. I tried reaching out to the hiring manager, no response, kind of classic situation there. But I got some interviews and met the people here and started out more on the industrial side, which I did for about 8 months. And then I transitioned to more of the commercial and industrial refrigeration role. So my first portion of work at Energy 350 was going out to various industrial sites around Oregon, looking at their whole system, their whole building, and trying to find opportunities for energy efficiency, and then passing it to other technical leads who would do the energy study and the energy modeling of those spaces. But then I kind of wanted to get more and more of my chops down for technical skills. And so I transitioned to the role I'm in now, where I go to a lot of commercial buildings, look at a lot of HVAC systems, and then also look at industrial refrigeration sites and try to find energy efficiency and energy saving opportunities, kind of similar to Solomon. Both of our jobs are engineering positions at the company, but our teams look at systems and the energy industry through a slightly different lens, which we'll go through. And I think both offer very helpful perspectives to anyone looking to get into this industry.
Absolutely. So really quick, what is Energy 350? So our company purpose is to use energy efficiency as a resource to offset the need to build new power plants and combat the climate crisis. And our vision, actually, and our president's vision, Chris Smith, is really inspired by Amory Lovins, who a lot of you probably know, the co-founder of the Rocky Mountain Institute. And the idea is that it's often far cheaper for both the customer and the utility to improve their energy efficiency than to generate more power.
One of our perspectives is that by connecting the dots of each system in the built environment, we can use engineering to mitigate our energy consumption. Our job at the end of the day is telling a before and after story with very limited information.
And yeah, lastly, we're a company of weirdos, but we get the job done and we have credentials to do it. So really quick, diving into strategic energy management, that's what I'll be talking through. I'm kind of opening off with this question. What if you could save 3 to 5% of a facility's energy use with the same equipment that they're already using? And that's a pretty great deal, right? Why wouldn't you do that? And that's what you're trying to do with SEM, Strategic Energy Management. So what is SEM trying to do? SEM's goal is creating and sustaining a culture of energy management within a facility and making energy management a core business practice. And I think it's really cool, and it's something that I wish that I had learned about when I was at Western. So I'm glad to be able to share with you all today. So what is SEM? It's a holistic approach to energy. So it's more than just project-based. It's similar to the idea of holistic health. It's the idea that everything is interconnected, from the people who work at the facility to the machinery operating there. And it's really focused on organizational change. And so the goal is to help customers make energy management a core business practice and ingraining it in their culture. And a major part of this involves educational workshops, technical support from our team, and getting buy-in from employees to make energy management practices stick. And it's really looking at energy savings throughout the facility. We look at the facility from a top to bottom and process by process approach to identify opportunities for savings. And these savings are actually measured through a top-down energy model, which I'll go into later what that is. And we're really focused on low and no cost measures. So we're thinking beyond like capital projects and helping them identify quick wins like set point adjustments, turning equipment off, fixing compressed air leaks, things like that. And it's cohort based. So we work with anywhere from 4 to 9 different companies in a single cohort. And they're all sort of learning together and working individually to help save energy. And what makes SEM different from a typical energy efficiency program? The main differences are that SEM is really focused on teaching energy management practices, behavioral change, and low and no cost projects, while a typical program would be more focused often on like equipment and controls replacements and retrofits. Additionally, SEM uses top-down regression analysis to measure savings, which I'll talk through soon what that means. While a lot of other programs calculate savings using bottom-up, like project-specific calculations. But both develop projects, quantify savings, and win incentives with the goal to reduce the operating costs for the customer and utility. So SEM started in 2012, so it's pretty young still, and it's growing. And so far, these are the main utilities that participate in SEM across the US and Canada. This will likely continue to grow as SEM gains recognition and support. So here is the SEM continuous improvement cycle, which is the backbone of our curriculum that we teach our participants. And we use this in tandem with other curriculum to work towards organizational change within the facility. So front and center is involve the right and more people. So the idea is organizational change requires collaboration and stopping to think about who should be involved. And we like to ask, like, how can we expand the reach of our efforts across teams? And then next is connecting with purpose. This is the why. So why is this work important to them personally and to their organization? Then we explore and prioritize. So these are the energy saving opportunities, right? We'll conduct energy scans. We like to call them treasure hunts, where we work with the facility to identify and prioritize key energy saving projects. And we do this in collaboration with them, walking across their facility. After the projects have been identified, then you're implementing projects, right? So once they're identified, it's time for rubber to meet the road and start making changes that result in actual energy savings. Once you've done that, then you measure the results and you adjust as needed. So did the project they completed do what they thought it would do? And this energy model I'll talk through later can actually help you visualize that. Then you kind of want to ensure persistence. So the idea here is if their whole team won the lottery and left tomorrow, would all of their hard work stick? And if not, how are we going to make sure all of this hard work sticks when they leave? And then lastly is celebrate success. So when you achieve savings, that's a cause for celebration. And that can be like a high five, prizes. For larger wins, it could even be like a barbecue to celebrate their achievements. And then, got ahead of myself. And then reconnecting with purpose. So scheduling periodic reviews to realign goals and keep momentum. And this framework can be used for process improvement anywhere and a number of other aspects besides energy management. We just use it for energy management. So now I wanted to dive into a couple example SEM projects so you can get an idea of what we do. So here, this was a quick set point correction for an aerospace manufacturing facility, which had really strict air pressure requirements. And so the rooftop units were supplying too much air to maintain a positive pressure in their space. So we slightly increased the outside air percentage and decreased the return air percentage, which allowed the rooftop unit to maintain a positive pressure with less airflow. And this also saved a lot on heating and cooling and dehumidification energy because this space also had really strict humidity requirements. And this saved 500,000 kilowatt hours a year. And it was a really quick, free set point change. It took like a few minutes to implement and started saving right away. So it was a really good, quick win for them. And that's about 50 homes worth of energy use for perspective. Another example project. So greenhouse was using excess lighting in shoulder seasons when it wasn't needed. And so this project was just to stop using supplemental lights earlier in the spring. And the site actually came up with this opportunity, and we just helped educate and empower the staff to make the change through workshops and regular meetings. And typically over 50% of the opportunities come from staff who are just empowered through SEM to implement their ideas. And this saved 400,000 kilowatt hours a year, which is the equivalent of 4.5 million tacos if you burned them in a power plant to generate this electricity. And this was also a really quick change. It took like 2 minutes and saved a lot of energy. So this example, a food manufacturing facility had a lot of compressed air leaks, which were causing its air compressors to waste a lot of energy, generating extra compressed air that's consumed by these leaks. And so what we did is we used an ultrasonic leak detector to identify compressed air leaks. And you can see on the right, those photos are photos from the ultrasonic leak detector. And basically it's heat mapping the sound of the leak. So you can actually visually see where compressed air is leaking. And air compressors are only about 15% efficient, which means 85% of the energy is lost as heat. And that makes compressed air very expensive to make and leak. So we found these leaks so that they could be fixed. It took about 5 months to fix all of these leaks, and it saved about 400,000 kilowatt hours a year. And that's about 22 million homework assignments if you burned them in a power plant, assuming 3 pieces of standard paper per assignment. I thought you students might support that as a form of energy. So moving on. So after you're implementing projects, how are we measuring energy savings? And this is something I was mentioning earlier, this SEM predictive model, but I didn't really explain how it works, and so now I can dive into that. So this is a tool that uses past data to make a prediction about future energy use. In this diagram, orange is the predicted energy use. That blue line is their actual energy use. And on that left side, that's the baseline period before they've started SEM. And you can see the blue line and the orange line are really close. Actual and predicted energy are nearly the same. Then they start SEM, and their actual energy use starts going below their predicted energy use. And that gap between the 2 lines, that's the energy savings. And that's what we're quantifying with this model. And something that's really cool about this is that it can capture energy savings from behavioral changes that would be really hard to capture through other ways other forms of calculation. So it's really helpful for SEM when we're teaching energy management practices and making behavioral change for energy efficiency. So how are we making these predictions? So to predict energy use, we create a model using single variable regression analysis, so statistics. And we look at major energy drivers and their impact on energy use. So first we have like a constant called the intercept in the model. And this is essentially like the baseline energy consumption for the site. Then for each energy driver that we choose, we get a coefficient to multiply the variable by. And these energy drivers can be like weather, they can be schedule, like holidays or weekends, or they can be like production, like, because we're working with industrial facilities often, so like toys that they're producing, trucks they're producing, food, or occupancy, depending on the building type. And every site is different, so they can have different energy drivers even if they're similar in the same location. But that's like kind of like the typical framework of a predictive model. So here's like a screenshot of an example SEM model. Orange is the daily predicted energy use. Blue is the actual energy use. And there's also this green line, and that's called the cumulative sum. And that's the sum of their energy savings. So it's based on the difference between the orange and the blue lines. So that's the steeper the slope of that green line, the more energy that they're saving. So you can see on the left side in the gray, that's the baseline period before they started SEM. And then they started implementing projects. The gap between the orange and the blue line is increasing as they're implementing projects. They're lowering fan speeds, reducing temperature set points. And as they're implementing these projects, that green line starts getting steeper and steeper. And on that graph, you can see they're saving on the right side over 3 million kilowatt hours through these projects. And so, yeah, as these projects are implemented, that saving slope gets steeper, and that's SEM really doing its work. And so now briefly, I wanted to talk through some of our curriculum that we kind of use to help find energy projects with the industrial facilities that we work with. And first, we start with the components of energy efficiency as a framework for looking for energy efficiency projects. The first item in this is size. So think like the rated horsepower of a motor or like the watts of a light bulb. The next is runtime. So like how many hours a day is this running? And then lastly is load factor. So kind of think like how hard is this equipment working when it is running? What kind of load is being placed on this equipment? And so once we're looking at that, we want to think about what percentage of energy use is being lost as waste, and can we modify any of these factors to reduce that waste? And so that framework, kind of along with the 5 simple savers, which I'll walk through now, kind of help guide how we look for energy projects and facilities, in particular industrial buildings. And so here's the 5 simple savers: turn it off, cut production waste, fix and tune your equipment, repair leaks, and optimize controls. And I'll briefly touch each one so you kind of understand what they are. So turn it off. This is pretty simple. Equipment uses the least energy when it's not running at all. So if it doesn't need to be running, turn it off. And that can be lights, process equipment, motors, HVAC systems, anything that's using energy. The next is cut production waste. So like I mentioned, we work with industrial facilities that are making a process good. And so production waste also wastes energy that was used to make that item. And so this can be like reworking or repairing defects, creating wasteful or unusable products, or unnecessarily moving or processing the product. That's all forms of wasted energy that we want to avoid. Next is like fixing and tuning equipment. So equipment operates most efficiently when all components are working and properly tuned. Dirty air filters are a really common example here. You can see in the photo, clean air intakes. So making sure your air intakes for your equipment is clean. Broken dampers, leaking valves, broken sensors. Fixing all of these will ensure that the equipment is operating like it's supposed to. And then the next one is repairing leaks. So by definition, anything leaking is wasted energy. In industrial buildings, compressed air is the big one. An air compressor is roughly 15% efficient, like I mentioned. So it's really expensive to make compressed air, and even a small leak can waste a lot of energy. Here you can see a 1/8 inch hole is costing nearly $3,000 a year in energy costs in this example. So really, really huge energy use. But it can also apply to like conditioned spaces, water pipes, vacuum systems. They can all leak. And then lastly, optimize controls. So often equipment is scheduled when it's first installed and it's not revisited. So this is really about like matching equipment operation to the hours that it's needed, adjusting set points within space and equipment requirements. In this example, here you can see there's an example schedule where the HVAC system is running normally on 4th of July when the site was shut down. So this would be like a really good opportunity for scheduling the equipment off on holidays so they can save some energy there. Another sort of set point example or controls optimization would be updating like compressed air pressure set points. Since compressed air is so expensive to generate, about 1% of an air compressor power is saved for every 2 psi that you reduce the air pressure set point. And that can really add up to a lot of energy savings if you can reduce that set point a lot. But also updating HVAC and process set points can also be really great energy savers. And now I'll pass it on to Hari. All right. Oh, let's see. There we go. All right. All right. So that was kind of like a great overview of SEM. A big portion of SEM, right, is that top-down approach that Solomon was talking about. And I think the beauty of this company is that we have a lot of people that sound like they have the same job, but in reality have quite different jobs. And so my day-to-day is almost the exact opposite in a lot of ways. It's looking at the individual component of a system and then breaking down that story, getting up to the whole building through understanding the whole system and how that impacts the whole building energy usage.
This is a great picture of my colleague and I staring at compressors for a cooling system, and both not having any information on how it's working and just taking time to process it, absorb it, look what's going on. So my day-to-day is trying to identify and quantify an individual problem that could be something along the lines of an occupant is saying it's too hot or too cold, something is not getting any airflow, whatever that is, and we have to quantify that somehow. So we have site visits. We are on site and we are observing the systems and observing the behavior of the system, and also the occupants themselves and the people that interact with those energy systems. We data log. We have these little data loggers that measure temperature, amps, motor on-off status. We usually do that over like a 2-week to several month period, and that gives us a pretty good snapshot of what a system is doing. And then we analyze it and communicate it to look at potential cost savings, incentives, and sometimes CO2 reductions. A large portion of our job, both of our jobs, is storytelling. It's explaining a before and after of what that after could be. It could be a predicted. It could be measurement and verification, where we actually verified through those data loggers that the energy usage and consumption of those systems has been reduced. And a very large portion of the job is being confused. I'm sure that probably translates to most of the jobs at our company. But that is just the nature of this work, is that you're going into a room and there's a dartboard. I'm a big fan of horrible analogies. You're going to a room with the lights off and there's a dartboard and you don't know how to hit the target. You don't know what's going on. That's how it feels a lot of the time. So site visits, I kind of want to break down what it feels like in person. The first thing beforehand is just kind of asking some basic questions. Why am I going? Am I contracted to look at a very specific system? Are they asking me to look at the whole facility and come up with some recommendations? What are we looking for? And then what systems am I expecting? Depending on the site, I could be expecting to mainly spend most of my time looking at air compressors. I could be spending my time looking at industrial refrigeration. I could be looking at HVAC. And so I kind of want to narrow down before I get to the site what I'm going to be looking at. Sometimes it's pulling up the site, if I don't know much information, pulling the site up on Google Maps and looking at satellite imagery and trying to get an idea of what kind of systems are on the roof. It's always kind of surprising to realize so much can be learned about a facility just based on like a satellite photo. And then who are you meeting with? Recently, I was supposed to be meeting with the facilities manager at a college campus, and I ended up meeting with their plumber because the facilities person was too busy. And so who you meet with really kind of dictates the site visit. What kind of questions can you ask, right? You have to suddenly start thinking through different channels, like what is their background? How are they approaching the system? What do they know about the system? And what information that they have can I get to help me get through this project? Some of the gear I take with me is basic tools. I take vests, helmets, steel-toed boots for safety. I take data loggers. I take arc flash gear to make sure I don't get zapped. I've never been zapped. I don't want to be zapped. I plan on not being zapped. I take a notepad. I take a phone for pictures. And I take a USB stick. Sometimes control systems for HVAC or industrial refrigeration, they have really good control systems, and a lot of these systems are set up to trend like data points that they have, whether it's temperature or pressure. And so if you have a USB stick, you can gather a ridiculous amount of information in a small amount of gigabytes or megabytes than you can in 2 weeks to several months worth of log data that I can get by putting my data loggers on. And for the phone, I will say, recently I've had coworkers that ask site contact if they can record the site visit just like via the voice memo and put into I think they use an AI tool and transcribe their notes, and it's extremely helpful to just have videos and photos and a recollection of what's going on, because when you're on site, that's the only time you're going to be immediately there in front of the system with the people that interact with it the most often. So that is just your best opportunity to gather information. So an expectation versus reality. I'm sure some of you guys have already experienced this if you've done any of the site visits to like the field trip class or any of the class where you go and visit the different buildings and see the different mechanical systems for each of the buildings on campus. There's kind of an expectation in your head of what something might look like, and then you see it and you realize just how confusing the real world can be. On the wishful thinking side, you hope that everyone shows up on time, whoever you're meeting with, whether it's facilities, an electrician, business side, contractors. Ideally, I get a few minutes in a quiet room to talk. I usually explain why I'm there, And I hopefully get a walkthrough with time for questions and photos of the systems. And yeah, in an ideal world, space is clean, organized, and safe. In reality, I have been forgotten several times by site contacts. I show up, they don't know who I am, they don't know why I'm there, even after I've explained it. Or they've been told by someone else that I'm coming and they still don't know why I'm there. And then the one person I meet with doesn't know about the system I'm trying to look at. So there's a lot of curveballs that you get thrown, and you kind of have to think really fast on your feet and be like, okay, well, this person is a plumber. I'm dealing with water in some way. What information can we overlap with? What Venn diagram exists that I can get some information from them, explain why I'm there, right? Trying to connect those dots. Often there's no time for a quick chat. You're just on the site visit, you're moving. And often there's loud machinery where every question results in a very loud what that doesn't get heard by the person you're asking. And often they're dusty, chaotic, and sometimes they can be dangerous, especially in the industrial spaces. Or if it's wet, if you're dealing with electrical systems and there's water, just standing water nearby, sometimes you kind of have to be like, well, that's electrical, that's water. I know those two don't go together, and just walk away or explain that you can't operate on that system if it's not safe. So some of the potential sites that you could interact with in this kind of job, on one side you have commercial buildings, on the other side you have industrial facilities. Most of my time is spent on commercial buildings, so I do a lot of office buildings, schools, college campuses, but we've also done hotels and resorts, municipal facilities. On the right, there are distribution and warehouses. When I first started at Energy 350, that was more of my time was working on industrial facilities. Currently, I still do some work with industrial refrigeration sites. But these are just kind of some of the possible sites, possible industries that you'll come across that use a very large amount of energy. If you can see it on the bottom, those charts are the energy by end use for two recent projects. On the left is a commercial site, and on the right is an industrial site. It's just a nice breakdown of kind of seeing how in a commercial site, HVAC is just such a large portion of the energy use. I will say that one, the large orange section is the space heating, and that was abnormally high at this building. Again, the point of our project was to go there and figure out why, look at the individual components and see what was breaking or not working, or some signal was not sending a signal to something else. And on the right, you can see that those plug loads, which is that big green section, are a much higher percentage. Those are made up from air compressors and various motors throughout this facility. It was mainly a distribution and warehouse. So you can kind of see just how energy is used in different ways by end use at different sites, depending on what they do there. A big barrier, and I think Solomon and I have kind of covered this, but a big barrier to energy engineering that I've encountered is going from the two-dimensional world to the three-dimensional world. Everything is often simplified on a control screen on that right side, where you get set points and you get status, and things are being very clearly explained. Even if something's wrong or maybe something's missing, it's relatively easy to follow along. This is a heat exchanger, and you have two pipes, and they're interacting in the heat exchanger and sharing heat. And then on the left is what actually it looks like, and you come in and you see this, and you have a side contact staring at you, you have a senior colleague staring at you, all expecting you to figure out what's going on. And oftentimes you just have to take a minute, breathe, and then look, and you will see that there's a labeling. It's kind of hard to see in the size of the photo, but there's labeling on a lot of those pipes. And if you just kind of look at the arrows and follow what's going on, maybe just focus on one pipe and be like, okay, what's that pipe doing? Where is it going? Why is it reading pressure? Why is it reading temperature? And try to understand each component individually rather than trying to have the big picture perfectly figured out. If you take pictures of everything, you can always come back later and think about it a little bit more to ask someone another question. But you don't have to have all the answers right on site, even though sometimes it feels like you do. But I just think going from the two-dimensional to three-dimensional is a very clear barrier that I've run into trying to understand energy systems in energy engineering. This is another continuation. This is a portion of a refrigeration system that we were working on. Oftentimes, it's all about flow. Heat, water, air, refrigerant, product, they're all going somewhere. Something's happening to them. And somehow, somewhere along the way, they're using energy. In this portion on the right, it's a portion of a refrigeration system that is called a subcooler. And we were trying to understand how to optimize this system. They just put it in, but they didn't commission the system and put in the right set point. So on the right is the actual physical system. In the middle, you have the controls and sequences of operation on the control panel. And on the left is the diagram that my coworker and I wrote up to try and explain what was going on. And oftentimes when you run into these site visits, you're looking at these systems, and you may have read about how the system works online, but how something works or how something should work and how something is working in person are going to be, that is the discrepancy. That is the point of our job, is to explain the misuse of energy, so to speak, by not doing what it's supposed to. But sometimes it's hard to have that engineering mindset of like, okay, what is wrong with everything that's in front of me, right? You're trying to look and be critical and try to ask all these questions, but oftentimes it doesn't make sense why something's not working. Sometimes it just looks like it's a pressure set point. Sometimes it's a temperature set point. But if you just slowly map it out and draw out each section, you can oftentimes get to the answer. You can break it down into different components. You can ask various people here that all have different pieces of knowledge and in backgrounds, and they're the side contact, and you can run it past all of them and get a pretty good understanding of, oh, okay, this is why this is not working. This is why it's wasting energy, and build the model from there, quantify the energy savings from there. Here's just an example of what our data logging looks like. On the left, that's a colleague and I at a distribution warehouse. We were trying to get inside this air handling unit, and little did we know until after you can see that we were both vertically challenged into getting that off, because the site did not have a ladder anywhere nearby. That once we got it off, we found out it was the wrong panel. In the middle picture is the actual panel, and it was much easier to access. It was at chest level versus me stretching as tall as I can at 5'8". In the middle, you can see an example of what our data loggers look like. It's that little white box on the right. It's got these little probes that come out of it. We can measure different components and temperature inputs of this air handling unit and get a profile of, hey, what's the system doing when it's hot outside? What is it doing when it's cold outside? And get an explanation as to why something might be broken. Is something not moving? Oftentimes, some actuator, some damper, some little tiny component somewhere along the way has failed, and that's leading to like an incorrect use, so to speak, of energy. On the right, that was actually today. I was at a elementary school, and I had to go into this door to Narnia. That was a hallway full of HVAC ductwork, and I did not know, I was picking up loggers, but I did not know that there was going to be students at this time. So while I'm up there on the ladder, I'm looking down on the ladder, the site contact is getting a barrage of questions from 6-year-olds that are asking, why are you here? What's going on? Is this the end? And somehow between the two of us, we're supposed to explain climate change, energy efficiency. Nope, that's not going to work. Let's just say we're looking at the fans. And we said we're looking at the fans, and the kid goes, I don't know what to do about that, and walked away. So sometimes you just have to kind of tailor tailor to your audience. In this case, I think there's a limit with how much you can explain to a 5 or 6-year-old. But yeah, that's often what a day-to-day site visit might look like. So I just kind of wanted to go over the foundation I feel like I've been self-reflecting on, of like what got me into this place. I think this presentation and this whole meeting, it's been a nice way to kind of think about, okay, how did I get to this point? What are the different components that led me here? The obvious one is that it's science. A lot of it comes down to science and engineering. But I've noticed ever since college that a big thing I had to learn was, how do I learn, right? I think for me, there's only so much I feel like I can learn from online, from research, but I oftentimes really value a mentor and a teacher, whether that's a professor or senior colleague, a site contact who's willing to explain something to you. It feels like finding spaces where you are allowed to ask a dumb question is very important. And I think sometimes it's ego getting in the way of not wanting to ask the dumb question. Sometimes it's fear of just being, awkwardly outed as the person who doesn't know what's going on. But once you ask, and this is I think people are realizing more and more with dumb questions, is when you ask a dumb question, you'll realize many people had that same question, but weren't either curious enough or were also scared to ask that question. So asking the dumb questions is extremely important. The internet is a big, wide, endless void of information. There are white papers, like academic papers that are out there. There are engineering forums. There's some very old textbooks, whether it's ASHRAE or some of the ones we read in college. YouTube is actually surprisingly helpful with the amount of information from like some sources like the engineering mindset. I think both Solomon and I remember a period when we were both referencing that, because the videos have great diagrams of what's going on, whether it's refrigeration or HVAC or electrical systems. So if you're just trying to understand the visual of what's going on, that's a great resource. Understanding the thermodynamics and the physics is extremely helpful. Understanding how a fluid is changing state, how it's gaining and losing energy, to the environment and to the components around it. All of that is extremely important. Sometimes, if I'm really desperate, I will use Reddit just to get a better understanding. Sometimes people will just be sometimes some HVAC engineer who's had 30, 40 years of experience will just happen to be on Reddit 4 years ago and post an extremely helpful context that is just like, oh, that's the exact wording. That is the vocabulary I needed to understand what is going on in this system. And then, of course, I've saved almost all of my college lectures just to reference some of the visuals, some of the understandings, trying to going back to those roots. Yeah, I think I just kind of wanted to like explain that questions I think are like just ever so more important in this job and also just in this industry, just trying to understand what's going on. Sometimes it feels like you're playing detective. You've got very random pieces of information. You don't know how they all connect. And you feel like it's kind of staring you in the face. And so oftentimes it's perspective, asking other people who have more experience or just different experience, how they would approach a problem. And between all of those resources, I would say you probably have the tools to figure out the model, figure out the problem, and provide an explanation to the client. This is a quick snapshot of what the kind of bottom up side of the modeling looks like. We do these things called 8760 modeling, which is modeling the 8,760 hours in a year. Most of my work I do via Excel. So do these Excel-based models that, especially with HVAC and refrigeration, are looking at outside air temperature and how that affects the energy usage of a system. These are just the inputs. On the right is the electricity calibration. For anyone that's calibrated a model, you know the deep satisfaction of even getting relatively close to the profile of a building energy use. It's extremely frustrating when you've got almost all of it at the very end. There's this weird tail that's just happened and you don't know why it's there and you can't explain it. And you've got to just spend time calibrating it. So that's kind of what a snapshot looks like. I think just to conclude, I think I want to talk about how connecting the dots is extremely important, whether it's the physical engineering that's happening or working with a client, working with a customer, or working with your boss, working with your colleagues, working with the internet. There's all of these different drivers. I've kind of outlined them. What I think there's plenty of drivers, but I think these are three big ones that immediately come to mind. Whether it's climate change, costs, policy and code, enforcing different changes in systems. And then in the middle is kind of what engineering feels like, at least in this job, where a lot of it just comes with on-site experience. You're using engineering and physics, but you're also trying to remind yourself, and I think this is one of the strengths of the not having the engineering degree, but having this pretty much any degree from Western, is trying to challenge yourself to think differently and approach a problem differently than how other people might. And how it comes down a lot to storytelling. It's like, hey, something is being affected by a person or something is just broken. How do I explain that at the end of the day? How do I explain my engineering and my assessment of the situation to this one person who does not have my background, who does not have my background in education, but has trade experience, who has finance experience, who has facilities experience? How do I explain this project to them? And the ideal output is that you're saving money for both the customer, the client. You're saving money for on the utility bills, and the utilities themselves can work with lower cost options. They have more energy to work with now because ideally we've saved them energy from this one site so they can sell that energy to a different site. Greenhouse gas reduction is obviously, if you are using any electricity or gas around here, it's most likely going to have CO2 or other greenhouse gas associated with it. And then, of course, occupant comfort and production efficiency are just the other two sides for commercial and industrial facilities. So between all of those, I think this is kind of how I would approach connecting the dots. I wouldn't say, this is not to say that energy efficiency engineering is necessarily the crux or the middle of all of this transition. It's more just, in my current role, this is kind of how it feels. It kind of feels like you're being pulled in these different directions and you're trying to use these different tools and these different resources to get there. So I think that's kind of where I would conclude it at. Yeah, oh yeah, let us know if you have any questions.
I think Darren's pulling up some questions.
Yeah.
Darren, did the batteries die?
Oh no. Oh no. Batteries ran out of energy.
Can you go to your other laptop?
Oh wait, we got something to chat. Pardon audio problems. No terrible feedback. Oh no. Oh no. Oh no. Oh no. I don't think I did that. Those are so shitty. Yeah.
While Darren's figuring that out, there are a couple questions in the Q&A. If you, either one of you want to look at the questions and see if you could answer them.
You want to pull up the question?
Yeah. I guess the questions tab. I'm trying to pull up the I feel so technically challenged. I don't see any questions in the chat. Is there another spot?
There is, so one of them says, does Energy 350 interact with Energy Trust of Oregon? And if so, how?
Yeah. So there are multiple ways. Yes, we do interact with the Energy Trust of Oregon. That's a big portion of our business and company is Energy Trust of Oregon, but we interact with them in different ways. So the main one is that Energy 350's main contract is being the managing contractor for the Energy Trust of Oregon. So Energy Trust is this big nonprofit essentially in Oregon. The way it works is on all customers, residential, industrial, commercial, on all of the utility bills. A portion in Oregon, there's legislation that says a portion for all the private utilities. All of their ratepayers have to pay a very small percentage of their bill, depending on your energy use, and that goes to this big pool of funding. So the larger, more industrial, commercial sites will pay more into this fund of money, and the smaller consumer level or residential level ratepayers will be using less energy and they'll pay a smaller portion. So there's this big pool of money. And the Energy Trust of Oregon basically has managing contractors for different divisions, whether it's commercial or industrial or residential. And they have a business, a company like ours managing each of those. And Energy 350 manages the industrial section. So we have account managers and energy engineers that are going out to all of the industrial sites around Oregon that are served by a public utility or a private utility that we work with, and offer them incentives and work with them for energy efficiency projects. We also do, my individual work is working on the commercial side. I'm on a smaller team at Energy 350 that subcontracts out to another managing contractor that manages the commercial side, and I do commercial energy studies for that company. Through Energy 350. So it's a little bit of a weird network, but the main point is yes, we do work with Energy Trust of Oregon, and we go provide incentives through Energy Trust of Oregon with that fund. It's complicated.
I think, can you hear me okay out there?
We can hear you.
Yeah, we can hear
Great.
you now.
Okay. I had cranked up the volume in here way too high and was getting some terrible feedback. So
Yeah.
thank you to all of you out there in internet land for being patient with me while I dealt with that. And thanks, Janine, for stepping in and helping with the Q&A there. I mentioned my ever competent colleagues on the foundation side. There's another shout out to them. So a couple of things that came up with, we've got one question in the room here. Thanks to you both, by the way, for a great presentation overview of how you got from being energy students here at IES to going out and changing the world one leaky air compressor fitting at a time. These are very important things, though. I had one quick question. I was impressed at your facility with the conversion factors, converting energy savings to tacos. By the way, I know of no power plants that are fueled by tacos, and homework assignments, but you didn't convert it to something that presumably matters to people in this room listening and your customers, and that's dollar figures, right? So we used to, back in the good old days, throw around the number of 10 cents a kilowatt hour for easy math. I think those good old days might be gone for a lot of the country right now. But when you talk about 500,000 kilowatt hours per year savings in that aerospace facility, give us an idea of what kind of dollars you're talking about for that facility.
Yeah, for that facility, so they're going to get dollars in two ways. They're going to get a utility incentive from working with us, and then they're going to get cost savings on top of that. Their specific rate, I think, is about 7 cents a kilowatt hour. So, maybe like $30,000 a year. And then on top of that, they're going to get about 4 cents a kilowatt hour just as a payment to them for saving that energy. So that'd be like another 20-something thousand dollars. Yeah, so it's definitely the cost is the large driving factor for this for sure.
Right, so that's not just chump change, right? $50,000 extra a year is something you can do some real work with, and it is of course in the interest of the utilities to pay them to find those savings, because as these gentlemen said a while ago, they can then repurpose that energy for somebody else where they need it. What RMI has long called negawatts, right? Finding those savings and putting them to use elsewhere. We had a question in the audience. I'll repeat the question.
I guess I'm the newest energy policy management student, and I was wondering how I can get involved with that. I'm also a resident in the Portland area.
So not to be too direct, but we have a job application coming to you right now. I'm kidding. We have a student who literally declared his major this morning in the energy policy and management degree, and is based in Portland, or lives in Portland in what you might call the off season. And so how might he get his best prepare for doing this kind of work? We talked literally this morning about how much of this is management, right? There's the science and technology, but a lot of this, and as you've said today, is about changing behaviors. So what advice might you have as two gentlemen who've been through this program for someone who's just starting out and might want to get his feet wet this summer even?
Yeah. The courses that I found most helpful at Western in the work that we do here, I would say would be the sustainable design class, the renewable power systems class, and also the open studio energy modeling class.
In the mechanical systems.
In the mechanical systems, yeah. I found that really helps with the technical side and understanding how to energy model, how to save energy, and how to calculate the savings associated with that.
Also probably thermodynamics, physics.
Yeah, thermodynamics as well. And a lot of that is covered in those courses. So I definitely recommend taking those courses if this is the type of field you want to go into. I'd also really recommend trying to get an internship while in college. It's a lot easier to get work out of college if you've gotten some experience while you're in college, and that was really helpful, I think, for both of us. So I would strongly recommend that if you can do that. And trying to get, I would say interpersonal skills are really valuable in engineering, and a lot of engineers maybe don't focus as much as that. So trying to maybe take some courses that might grow your skills there. Like I did a storytelling research project while I was at Western, and I found that to be helpful for me. And trying to kind of expand your skills there as well, I think is really valuable.
Yeah. I think also okay.
No, go ahead, Harry.
I think I was just going to add to that. I think, like, I mean, if there's like information outside of the classes you're interested in, or you're wanting to kind of dive deeper from the classes, I think like resources that get you connecting the visual systems, not even as much like how they look in person, just like the two-dimensional, even just like trying to understand the connection between like the built environment and like physical mechanical changes in equipment, as well as the on the other side the energy like flow. How is energy being used when mechanical systems are operating? So I think between those two kinds of resources, I think, or like recommendations, I guess, I think you slowly want to build up an image in your head of how energy is being used. I wouldn't say I have a perfect image. There's always going to be some component of a system that doesn't make sense to me, but asking the questions, figuring out how to ask the right questions, the right people, I think those kinds of both interpersonal and technical skills are extremely valuable here.
Yeah, and then definitely, I forgot to mention the energy auditing class. Take that as well if you want to do energy auditing work. It's super helpful.
This sounds like a lot of the work that Nipun Goel, one of our professors, is indeed doing with his energy assessment program. The air compressor story reminded me of one where he took students out to a facility, a manufacturing facility in Whatcom County. And without any fancy detecting equipment other than ears, you could hear the air leaking from various hoses around the facility where they're using different air tools. In addition to that, went out back and the air compressor was housed in a little shed to protect it from weather. But when you walked into that shed, the temperature in there was 20 degrees hotter than ambient air outside. And of course, hot air is less dense. That compressor is having to work harder to compress that air. A vicious cycle of further increasing the warmth of the room. And wearing down the air compressor before its before what would have been its normal lifespan. All of this fixed with a piece of 6-inch PVC to bring cool air into the $20 of PVC or something like that.
Yeah,
So
I mean,
low hanging fruit.
Yeah, I think to add to that, there was something I remember when I started going on sites with this company that I remember learning in one of Nipun's classes, which was like sometimes stopping and just listening is extremely helpful.
Yeah.
Or just like using your senses, like whether it's pressure, like you try to open a door in a building and it's either really hard to open or super easy to open. Like there are small things, these small indicators that give you an idea of, okay, well that shouldn't be happening, right? I shouldn't be hearing air. I mean, sometimes it could just be sound acoustics, but if you hear an air handling unit upstairs or something, you shouldn't be hearing that. But like, there are just situations where you're hearing something, or the air is extremely hot and humid and it's dry outside. You know what I mean? Like something is going wrong, and trusting those instincts or building up those instincts to trust is extremely helpful.
Yeah, and the people who work at the facility are probably used to it and they experience it every day, so they don't even think about it. They're like, this hissing noise from the compressed air leak. That's just what
normal.
It sounds like.
Yeah.
Like there's not actually any leaks.
Standard operation.
Yeah,
that's
what it sounds
yeah.
like. And so like coming in with an outside perspective can be really helpful for that.
So here's that maybe leads into this next question from a student in the class. It says, what's the key difference between strategic energy management and how we manage energy traditionally? And maybe that is just sort of the set it and forget it and get used to the building being too hot or too cold, or hearing the hissing of leaky air compressor fittings and whatnot. But maybe you've got something more to say. You said you talked about SEM as a thing taking off a little over a decade ago. Maybe remind us at least of what the key characteristics are of SEM as a practice.
Yeah, I think some of the things that really set it apart from other energy efficiency work is, like you mentioned, it's not like a set it, leave it sort of thing. So it's not like a lot of energy management might be like, oh, we're gonna fix these leaks and that's it, or we're gonna like replace this equipment or upgrade this controls. But with SEM, it's a lot more focused on education and like teaching facility energy management practices so that it continues after you leave, they continue to save energy. Um, and it's also really focused on projects that are like free or really cheap. So they're like really quick wins that can be implemented easily. Like fixing leaks was the example that I used, but there's a lot of other like set point adjustments or heat reuse or lots of ways you can cheaply save energy that maybe are low cost. Um, Yeah, I would say those are kind of the like it's really about that key of like sustaining energy efficiency within the organization and kind of making a culture of energy efficiency within that organization and making the people working there sort of continue that on when you stop working.
Great. Yeah, and that reminds me, you mentioned Amory Lovins and Rocky Mountain Institute. Amory's a friend and mentor of mine, and a lot of RMI thinking about systems thinking and efficiency is really baked in to the curriculum here, thanks in part being to my predecessor also being an affiliate of RMI or a longtime principal there, and the I guess the commitment to thinking about a system, whether that system is a building or a city or an air compressor or a cooling loop, as a system that performs, right? And so to your point about coming back and reassessing rather than setting and forgetting, I think that's important. Second question from another student. Super cool. Thank you guys for taking the time. I'm wondering if you guys will be hiring any graduates within the next 6 months or so. I see right now there are count them, two positions for energy efficiency engineer advertised on Energy 350's website. Seems to me that there's a preference for folks with a little more experience beyond the undergrad degree. But what can you say about maybe internships that might be opening or positions for students coming out of, say, the only energy program in the country like this that you might know, how to best position themselves for this kind of work maybe?
Yeah. I know that we do have a summer internship that I don't know if I think it could pop up on our website in May, but I believe it's like June through August kind of internship. For the positions, I would say they always encourage people to apply because they usually keep applications. So it's like, yeah, worst comes to worst, they're not hiring exactly for a recent grad, but they will keep that name and they'll keep that file. I think it depends. I think one of the positions for sure, I would say if the best chance you're going to have, I've talked to some of the hiring managers here. And just for context, I guess almost everyone at this company, I think until the last couple of years, but almost everyone at this company, it's about 70 people now, are engineers. Even the people that like manage like the HR side of things and business side of things. The president is an engineer. He still does his engineering work day to day. So like that's just the context. Is like that's kind of one of the things that makes the company different. Is like most of the people are just pretty logical and approaching things as most mechanical engineers would, including the people hiring. And what I've talked about with them is that any position that they don't explicitly state as more senior in the Portland area, because that's where the company is headquartered, is usually open to more recent graduates because they have that time and they have that ability at the office here to mentor and to grow people while they're here. In some ways, I mean, both of us, even though we had experience at other places, are still junior engineers. And so, kind of being in this local headquarters area, they can have the senior engineers kind of walk us through different things, and we can have that exposure and build up that experience rather than expecting you to come in. So I would say the best chance is going to be the Portland jobs. And out of those, if they're not explicitly stated as a senior position, there's usually a good chance they're open to recent grads.
Great. All right. Well, that's an optimistic and happy note to end on. So I don't see any more questions from the interwebs and no more in here. So I will thank you two once again for taking time out of what I'm sure is a busy day and sharing your experience with us. Great to see you both again, and I look forward to the next time seeing you in person, maybe up here this way or down in Portland area.
Sounds good.
And we will sign off. Thanks for joining us.
Yeah, of course. Yeah, have a good one.
Thanks. Take care.